last time I introduced you to the fundamental force law of magnetism. The answer to the question of if I have a charge here, Q, moving with velocity v in this direction, what magnetic field does this charge produce at this location? And the answer, given here, we walked through last time, the magnetic field is proportional to how much charge there is, Q. And it depends on the velocity, and it depends on r hat, but the way it does so is v cross r hat. So in particular, it depends not only on the magnitude of v, but the direction of v. For example, if this charged particle were moving this way, then the sign of the magnetic field would flip, and instead of pointing from you towards me, it would be pointing from me towards you. Now, the other thing which the v cross r hat does is it sets up the pattern in space of how the direction and the strength of the field vary. So the field on this side over here is going from me towards you. On this side over here, it's coming out from you towards me, coming from you towards me. And its magnitude at a given distance r is greater over here. As it gets less, it gets less. All of this we talked through last time. Now, to take this force law and put it into the form that is named after two French physicists, Biot and Savart, we need to ask not just about one little charge moving, we need to ask about current in a wire. So if you start to think about a wire with current flowing down it, there's lots of bits of charge in this wire. They're all moving in this direction. In other words, I have a current I. And I think about each of these little bits of charge Q, each of them makes a magnetic field according to this force law. And now I use superposition. I vector add all the magnetic field produced by all the little bits of charge that together make up this current. And when I do that, I'm going to get a magnetic field which looks as shown in this diagram here. The magnetic field curls around the wire, and it does so according to a right-hand rule. If I take the thumb of my right hand and send it down the direction of the current, the direction of the magnetic field is the direction in which my fingers curl. So the magnetic field curls around the wire like this. That is inherited from the force law over here, where if I had taken my thumb along the direction of the velocity, the direction of the magnetic field curls around that velocity vector as we discussed last time. So if we compare and contrast the electric force to the magnetic force, if I imagine that instead of carrying a current, this was had a charge density along this wire, then it would be a source of electric field. If I had a bunch of charge along a wire like this, then it's a source of electric field, and the electric field points radially outward. It points away from the wire, or it points radially inward. It points towards the wire. It doesn't point around the wire. Once I have a current running through the wire, instead of asking, given a charge here, what electric field does it make? I ask, given a current here, given moving charge here, what magnetic field does it make? I get the answer that we've shown here, which looks quite different. The vectors are pointing in a different direction, and this difference in the direction is really the essence of the difference between magnetic forces and electric forces. So what we want to consider now is a wire, and it might be straight, like the one in this diagram here, but the way I draw it on the board now, I don't want to assume that the wire is straight. So here's a wire, and it's carrying some current I. And in this wire, there are lots of little bits of charge. And let's focus on one little bit of charge here, which I will label dq. Here's my dq. There's a little bit of charge right here, dq. And this charge is moving. It's moving with some velocity in this direction. This velocity we've been calling v, but I'm going to call this velocity, I'm going to break this velocity down v, and I'm going to call v ds dt, s being a position vector. And so if I pick a point, where's my point P going to be? Let's say I pick some point up here. Here's my point P. And I ask, what is the magnetic field at this point P? Well, this magnetic field is going to be a sum over lots of little dBs. There will be a dB produced here by this dq, and there will be a dB produced at this point P by this dq over here, and there will be a dB produced at this point here, at this point P by this dq over here. There's a dq that's moving this way here. There's a dq that's moving this way here. Each of these little dq's is going to make a dB at this point, and then we're going to have to add up all the dBs to get the actual magnetic field at the point P. So what is our dB? Well, let's focus on this dq that we started with. So here's my dB. Well, what's it going to be proportional to? Given what we saw before, dB is going to be proportional to dq. Remember that for the fundamental force law that we had before, the magnetic field at the point P was proportional to the source of charge, and the source of charge here for us is this dq. And then it's going to be proportional to V. We're writing V as ds dt. So that's this ds dt right here, cross r hat. And what's r hat? Well, r hat is the unit vector pointing from this dq in the direction of the point P where I'm working out the magnetic field. So if I was talking about this dq, I'd have an r hat that was pointing from here towards P. When I'm talking about this dq, I have an r hat that's pointing there. For this dq, the ds dt vector points this way. For this dq, the ds dt vector points this way. The r hat vector points this way. In this particular case, for this dq, ds dt points this way, and r hat points this way. And this is my expression, or at least the beginnings of my expression, for the dB, the little bit of magnetic field caused by this little bit of charge. This little bit of moving charge, what magnetic field does it produce there? That's this dB. OK, and now I play a standard physicist's trick, and it's the same physicist's trick that we used previously when we talked about the force on a current-carrying wire. And I'm going to do it with my eraser here. I'm going to take this dt, and I'm going to move it here. So I moved the dt from under the ds to under the dq. And why did I do that? Well, I did that because dq dt is the current I. So the conclusion that I reach is that dB is proportional to I times ds vector cross r hat. So I have now, the way I'm thinking about this is I have a little segment of the wire right here. I'll do it in red. Here's my little segment of the wire right here. This is my ds vector. And there's a current flowing through this wire, and that current is I. That I is in front here. And then I have this ds vector crossed with the r hat vector. And we're almost done. To finish this, to make this into an equality, I just remember the other bits of the fundamental force law that I didn't yet write down. So if I want to make this an equality, I need to have a mu naught over 4 pi. And I need to have a 1 over r squared, where r is this distance here. It's the distance from this point here to this point here. And this is called the Biot-Savart law. In English, Biot-Savart. In French, Biot-Savart. Named after two 19th century physicists who were among the early pioneers of electromagnetism. So what we'll then need to do if we want to work out the mathematical result for the current around a wire like this is, here's my expression dB. And I need to add, if I want to know what the magnetic field is at this point here, I have to add up all the little dBs from this section ds, 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 this section ds. When I add them all up, the magnetic field that I get there will be the one shown by the blue vector, and it will. The direction is easy to work out if I have a straight wire like this. The direction is easy to work out because all of these ds cross r hats point in the same direction. And the direction they point in is obtained from the right-hand rule. I take with the thumb of my right hand, and then I curl my fingers, and that tells me the direction of the dB. In fact, it tells me the direction of all the dBs. Doing the math of adding up the dBs is something we'll do in a future video. But this then is the essence of how moving charges, which is to say current in wires, make magnetic fields. And everything that we're going to do in the next section of 802 is built on this plus superposition plus one more little fact that we haven't emphasized yet, but that we're about to get.